There are a number of significant bottlenecks associated with floating wind. We're talking about putting something about the height of the Eiffel Tower with a base that is roughly similar to the size of a football pitch. Reliability needs to be ingrained into the whole process. So in order for this to work, you really need the best thinkers in the world.
There are multiple challenges along the way that we need to overcome. Every step of the way that you're going through this cycle.
Each blade is 120 meters long or 400 feet long and has a turbine on the top that weighs about 700 to 800 tons.
It's one of those challenges that requires many, many heads coming into it. There's no one set of codes written out. People don't know the full answers yet.
So far, there are a handful of test sites for floating wind. The biggest one so far just has 11 turbines, that's in Norway. In the UK, we have a couple of sites with 5 turbines each. The plans at the moment are for something in the order of 2,000 new turbines within the next few decades. The UK is lucky to have shallow coastal waters around us, so we've been able to develop fixed offshore wind in shallow water. Most countries don't have that, so many countries are going straight to floating wind as a solution.
Just look to the west of us. Ireland is a good example. West of Ireland, everything there will be floating wind. Also France, Norway, Korea, Japan, Philippines, so it has global application.
There are 3 key areas where HR Wallingford can provide expertise into floating wind, whether it's development of the ports to facilitate the deployment of the floating wind, development of new tools looking at metocean impact on fatigue on the structures and the mooring lines, but also even things like the logistics for the whole process of assembling the units and then getting them out into the field.
I think there's a main challenge when you come from land to sea in the assembly port and putting it together, and the logistics there of taking these very deep draft assemblies or floaters, handling those in probably shallow facilities. There's a challenge there with the land space.
Each one of these needs to be constructed in ports which haven't been designed to build these, and also be manoeuvred into their final locations. I think for me the big challenge is how do you do kind of repeatability and almost a production line of these platforms and stuff going out.
We bring together the skills of hydrodynamic engineers, hydrodynamic modelers and really skilled navigators. And in the ship sim we bring those skills all together in one place to help people understand what the implications for operating such large structures in confined areas will be.
You need also to have storage space in vicinity of the port for the reason of in the winter you can't deploy them in field due to the weather conditions. These big beasts, and they are beasts, need to go out of the port up to a bay area that has sheltered from open sea where they're going to be stored.
When you put a 30,000 ton block in the sea and you get it moving without its own power because you pushed it, you've got to know how to stop it, you've got to know how to handle it and move it around.
The conditions are extremely challenging. The tip of the blades of these wind turbines are rotating at extremely high speed, maybe 180 to 200 meters per second. And even simple rain droplet hitting these structures can cause damage to the leading edge of the blades. Even the UV light from sun should be considered.
Each of these turbines will need to be anchored to the seabed with mooring lines. So because of that, there's likely to be a transition to use of synthetic mooring lines rather than chain. With synthetic mooring lines, there is a fatigue issue. Coupled with that, about 250 meters up in the air, you have this nacelle, the gearbox, the turbine. That is then waggling around, that generates huge forces. We are looking at new methods for evaluating that fatigue. There's going to be an enormous increase in the number of structures in the sea, and noise will be a significant issue during installation.
Sound underwater is the equivalent of seeing in air. So the animals use the sound to locate prey, They use it to communicate, to detect predators as well. So it's vital that they can actually hear the sounds around them. We model that noise, we determine the source levels of the sound at the pile, and then we propagate that noise in a mathematical model through the water. The work we do informs developers to make the right decisions to reduce the amount of noise that they're generating.
With our planned deep water tank, we'll be able to expand our capabilities in testing of floating structures at a bigger scale with a higher level of fidelity than we can currently do.
The wave generation basin will be 40 by 40 metres width, and then we'll have a movable floor that will go down to 5 metres depth. It will be really important for us to be able to have a high accuracy physical modelling of these full floating offshore wind platforms and mooring configurations at scale.
The rate of failures from offshore wind are going to be much higher unless it's properly tested and run through, and we can apply the best and all of the knowledge available to bring us to the right solutions.
As an engineer, you want to solve the challenges, you want to come up with solutions.
It's not traditional fluid mechanics, it's not traditional solid mechanics. You need understanding of both. So we are in a unique position to be able to help the industry.
So it's about planning and designing processes that are reliable. And that's what HR Wallingford is all about.